Hey everyone. A big jump in grade 5 is going from just talking about fractions and maybe, in some cases, comparing them to one another, to actually working with them. Now that means that in my class, we begin to add and subtract fractions for the first time ever. Now, most of the time, especially in grade 5, these fractions have what we call like denominators. That just means the same number on the bottom. If we're adding or subtracting one group of fifths, the other number we're working with will also be blank fifths. This is where we're going to start, but you'll pretty quickly see that this concept is simple enough that we'd be done with that in about 30 seconds. So we're going to go a little bit further this time as well. Still, best to start with the basics. Now, a common issue, and a big sticking point for a lot of our younger mathematicians out there, is that each of these numbers has two numbers in them. That way, the way that we write fractions is the biggest hurdle in a lot of ways to understanding them. Many students read these as two separate problems. This example I'm putting up top here. Let's take a look at that one. And since I used the example of adding fifths before, let's add fifths. Here we've got 1/5 plus 3/5. Now, the first instincts that most students have, especially in grade 5, when they look at this problem, is to treat it as two problems that happens to have a line dividing them. 1 plus 3 and 5 plus 5. This is the way they've been trained to read these problems for years by doing simpler stuff. Now the line is there, but what it means doesn't really register to them, so they will just keep the line in there and put one answer on top and one below. They're going to get something that looks like this. Now the catch here is to wrap our heads around the idea that the 5 in these problems isn't a number, really. It's a unit. We are counting fifths, but the number 5 isn't important to the problem. To give an analogy, if I was counting centimeters, every single one of my students, by the time they get to my class, is always able to tell me that 1 centimeter plus 3 centimeters is 4 centimeters. Well, in the same way, we need to get ourselves used to thinking of fifths not as a number, but as something we count. Early on, I find it helps students to write it out in words. This makes it a lot more clear that we're just adding 1 and 3, then throwing the word fifths on the end the same way that we would with centimeters, or if you're in first grade, counting 1 orange plus 3 oranges is 4 oranges, if they're doing a word problem about fruit. So, after a bit of practice, students start to get the hang of this and realize the following. When adding or subtracting any fractions with the same denominator, the denominator stays the same across the entire problem. Only the numerators get used. This means that if I'm subtracting 4 sevenths from 5 sevenths, I'm just subtracting 4 from 5 and using a 7 as my denominator across the whole problem. If I'm adding 12 twentieths to 5 twentieths, I'm just adding 12 and 5 and putting a 20 for my denominator across the problem. It really is that simple. If a first grader can subtract 3 apples from 7 apples, they can also subtract 3 ninths from 7 ninths. They just don't really have the language to do that yet. Now, however, we start to run into a problem. When the denominators don't match, we don't yet have a strategy in place to deal with this. By this point, students are comfortable adding and subtracting sevenths to sevenths as they are adding and subtracting cookies from cookies. But if I start talking about adding 2 sevenths to 5 14ths, they look at me like I want them to add cookies to orangutans. And to a degree, they're right to. If I'm not adding and subtracting like with like, this really doesn't work. But it's not cookies and orangutans bad. Rather than adding cookies to orangutans, it's more like adding centimeters to meters. 14ths and sevenths are two different things, but they're two different ways of measuring the same thing. Just like centimeters and meters are two different things, but both of them measure length by splitting them into different sized chunks, 14ths and sevenths both measure parts of a whole. They just split that whole into different sized chunks. I can add centimeters to meters, but first I have to change one of them. I have to take one of those numbers and convert it into the same type of measurement as the other. If I'm adding 25 centimeters to 3 meters, my first step is to make both of these numbers centimeters. 25 stays the same, but 3 meters changes to 300 centimeters. Once they're the same unit, I can add 25 to 300 very easily. So the extension to this is that there is more than one way to write a fraction. And one of the very first videos I ever made was about the concept of equivalent fractions. So you may want to go back and take a look at that to refresh yourself. I'll link the video in the description for a full refresher. The very short version is that by ensuring that we multiply or divide our numerator or denominator by the same number every time, both of them, we can create an infinite amount of new fractions that mean the same thing as the one we started with. If I start with 1/4, I can multiply both the 1 and the 4 by 5 and get that 1/4 is the same as 5/20. So let's go back to that problem with the mismatched denominators. Well, if there are infinite ways of writing equal fractions to the one that we have in front of us, sooner or later, there must be a pair of equivalent fractions that have the same denominator, and we can solve our problem just as easily as we could add any of the earlier ones. The first thing to check is to see if one of those denominators is a multiple of the other. So here's the problem written out. Looking at it, we can see the numbers 2/7 and 5/14. And if I know my times tables, I can probably see where this is going already. As I already said, the first thing I want to do is look at the smaller of my denominators. In this case, 7. Is there anything I can multiply it by to get the larger denominator, 14? Well, I hope by grade 5 you know that absolutely there is. I need to multiply 7 by 2 to get 14. So I know there's an equivalent fraction to 2/7 that can be out of 14ths. 2/7 equals some number of 14ths. Since 7 times 2 is 14, this tells me I can multiply my numerator by the same thing. 2 times 2 is 4. 2/7 equals 4/14. 2/7 is the exact same thing as 4/14. Well, that means that in my original problem, I can keep the exact same meaning for the question by replacing 2/7 with 4/14. Let's do that. Four 14ths. But now, nothing has changed about this question except the way I've written it, and it suddenly seems a lot simpler. 4 cookies and 5 cookies is 9 cookies. 4 centimeters and 5 centimeters is 9 centimeters. So, 4/14 and 5/14 is 9/14. 2/7 plus 5/14 is still 9/14 because 4/14 and 2/7 mean the same thing. The answer to the problem I put up earlier is just 9/14, and all I had to do was change my 7ths into something with the same denominator as the other part of the problem. Now sometimes it's not going to work out quite so cleanly. Take, for example, a problem where we're subtracting thirds from quarters. Now keep in mind, adding and subtracting any fractions with unlike denominators is already past grade 5. And for this next part, we're jumping well beyond the grade 5 curriculum. This is for the curious or those in higher grades who just like to see me explaining things for some reason. Now there is no way I can turn my thirds, my lower denominator in this problem, into quarters through one simple multiplication problem. Sometimes we need to find equivalent fractions to both of these parts of the questions in order to find an answer that works. Now the quickest and easiest way to solve this one is to look at the denominators and multiply them by each other. If I multiply 3 and 4 by one another, I'm guaranteed to get a number that's a multiple of both of these numbers. In this case, 3 times 4 is 12. So I know that I would be able to get an equivalent fraction of both of these that's out of 12. Both 3 and 4 can be multiplied by something to get 12. So I can find an equivalent number of twelfths to quarters and thirds. Now, for 4, this means multiplying by 3. 4 times 3 is 12. So for my denominator, going from 3 quarters to some number of twelfths, I multiplied by 3. Well, that means that for my numerator, I also need to multiply by 3. 4 times 3 got us 12. 3 times 3 gets us 9 twelfths. That's equivalent to 3 quarters. That's our first number. For 2 thirds, I had to multiply my denominator 3 by 4 to get my new denominator of 12. That means I need to multiply my numerator by 4 as well. 2 times 4 is 8. So 2 thirds is equivalent to 8 twelfths. That means that in my problem, 3 fourths minus 2 thirds, I'm actually just asking 9 twelfths minus 8 twelfths. And any first grader can tell you, if I have 9 cookies and I give away 8, I have 1 cookie left. 9 centimeters minus 8 centimeters is 1 centimeter. So 9 twelfths minus 8 twelfths is 1 twelfth. Since those fractions mean exactly the same thing as the problem I started with, I can also tell you, from knowing this, that 3 quarters minus 2 thirds is 1 twelfth. Whew. Alright, that's quite the extension over what we started with. But hopefully the steps along the way made sense. The first concept, adding and subtracting when the denominators are the same, is actually all you need in 5th grade and is super simple. When we started working in our understandings of equivalent fractions, we went well beyond what's expected of your average 5th grader. And well beyond what's expected of your average 1st grader. So don't be alarmed if it was a lot to take in. Hopefully the big ideas made sense. And as long as they did, doing the smaller steps to get you there will become easier and easier with practice. You'll have years to do that. That's it for today, guys. Now, if I have 1/5 of my fingers, and I add another 1/5 of my fingers, what do I have? Peace.